Hello everyone, we are team number 12 and the project of topic is application of neural networks for trade signal generation in VX futures. Problem statement. Our problem statement is to generate trade signals in VX futures, which stands for volatility index futures, by approximating the expected utility function using deep feed-forward neural network and recurrent neural network. Motivation. VX is used as a fear gauge as it suggests markets participant sentiments. In 2004, the Chicago Board of Exchange introduced VX futures and later on its options. VX derivatives are one of the most liquid assets in the financial world. The shape of the VX future curve is informative, however, it is likely to persist for a short period. The fluctuations are spontaneous and can generate a profitable trade. However, most trades involves non-zero probability of losses. Hence, if we can optimize the expected utility function with multiple trading opportunities, we may experience fewer losses. For a stationary VX curve, the action that will maximize the expected utility function under a probability distribution is given by A of x is equal to maximum of E of u of rt plus 1 of A, where u is the expected utility function, t is the denoted time, E is the denoted expected value, and rt plus 1 of A is the change in position from time t to time t plus 1 if action A is taken, given that we know the path of the function. The equation 2 gives the linear utility function U of r. The expected utility function is estimated using a deep feed-forward neural network and can be made more accurate with recurrent neural network. Model description. We are using an autoregressive model which can be represented by mu of AVT plus ZT plus 1, where ZT is an independent Gaussian random vector with mean 0 and covariance E. A is the least square estimator. Using the AR models, we can find the value of the rolling portfolio and hence the expected utility function. For the feed-forward neural network, we used hyperparameters configured at 500 epochs, 0.1 dropout rate, and sigmoid activation function, which was 5 layers of the dense feed-forward network as suggested in the trading signals of VX futures paper. A time series or time step dimension is added to create the required input shape for RNN. For RNN, we use sigmoid as activation function here. Other parameters are 500 epochs and 5 dense layers. Dataset description. The dataset is taken from the website vixcentral.com. The VX futures price with 1 to 9 months maturity is used for the time frame between 14th of April 2008 to 31st December 2020. There are a total of 3204 rows and 22 columns of raw data. From this data, the values of constant maturity function, the rule, will be computed, which will be our parameters of for x of t. Methodology. While dividing the dataset, we use 50% for training and 50% for testing the model. As we are considering a very large scale of data points to prevent overfitting of the model, and also considering the number of trade opportunities, we choose a 50:50 ratio. Evaluation of models will be done based on portfolio return, Sharpe ratio, and maximum drawdown, which will be computed by defining a time series portfolio. We are comparing all three models based on the rolling portfolio going short on 1 month and long on 5 months period on VX futures. The final objective would be to estimate optimal expected utility function and create trade signals for VX futures, which will be evaluated based on parameters mentioned previously. Results. Training loss and training accuracy started to improve from 0 to 100 epochs for both DFN and RN. The plot of DFN and training accuracy suggests that after a certain point, training accuracy converges for selected hyperparameters, and the same can be said about the training loss. On the other hand, we observe that validation loss is also reduced and converges after certain epochs, but validation accuracy is behaving like noise, or in other words, it doesn't converge. In the case of RNN, training accuracy and training loss improved instantly with respect to the number of epochs, but we can say that training accuracy is lower and training loss is higher for RNN compared with DFN. Also, validation loss is not converged to a fixed level, it also looks noisy. For both models, in sample and out of sample ROC curve suggests that we are not choosing randomly and our model is doing something better than just guessing. The ROC curve for both models looks almost similar, but the mean and optimal point in sample ROC curve for DFN are close, but the median is relatively at a distance. Whereas in the case of RNN, the mean, median, and optimal points are almost at the same position in sample ROC curve. The out of sample ROC curves for both models are comparatively at lower level than in sample ROC curve, but still suggests that the model is doing more than just random guessing. For both models, the optimal point on out of sample ROC curve is at middle and mean is at optimal point and median is below. Evaluation. To evaluate these models, a rolling portfolio is created and a time series of values of the trading signals portfolio is used. Performance metrics such as portfolio returns and maximum drawdown are computed using these rolling portfolios. The value of portfolio of trading signal generated by DFN model is consistent with that of AR model portfolio, but after that the value of portfolio of DFN model starts increasing more compared with AR model, which suggests that DFN model performs better than AR model on out of sample data or validation data. Similarly, the rolling portfolio constructed using RNN model trade signal is consistent with AR model portfolio for training period, but for out of sample period, the RNN model outperforms AR model by large margins. At last, DFN, RNN, and classification tree models are compared with the rolling portfolio of going long on 1 month VX futures and short on 5 month VX futures. The future scope of this project is to improve these models by using more large data sets, and we can use fractional Brownian motion to generate a path that will have some memory involvement. The results are mentioned in the matrix below and references are stated.